And to you guys, you're the ones here. Wendy. An exception. There you go.
Thank you.
All right, so today we're going to go more into this data path problem. So we've now spent a couple of lectures kind of going over the whole data path. The previous lecture we spent relating it to code. Now what we're going to do is we're actually going to break down and actually see how this data path is actually designed. So the best way to do that is to talk about what would happen if I want to reduce the data path. Because before, what you could do, actually the best way to do it is just bring up a Word doc, right? If I just said draw the MIPS data path on the exam, then I would be giving a problem that only really benefits people who are good at memorization. And you guys are not electrical memorizers, right? You're electrical engineers. So I'm designing the problem to be more reflective of your eventual career. So this problem, example 7.1, we're going to go through a number of these. Draw a MIPS single cycle data path that implements R-type instructions only. So not only are you going to do that, but you have to understand what each part does. So we're going to be going through that. So the best way to do this is to just take what you know about the data path and include parts that you do need, get rid of the parts that you don't. So what's the first thing that we have? Okay, no, it is an R-type. I'm asking you for the R-type. If you're drawing out the data path, what's the first thing you got?
Program counter.
Program counter, PC, right?
And then PC plus 4.
Yep. So PC. Oh. So you got something coming in here. You got PC, and then you've got this going out here, and then 4, right? So where does this PC value go into? We'll call it read address for short. So you got instruction memory, and then you got some sort of 32-bit value coming out here, right? So what's next? What comes out here? What do you need to draw? I would say, yeah, this is where it splits up. So my advice to you, first thing you should do when you get to here, draw your control, right? What will happen, I've told you this before, what will happen if you leave, when I give you the data path problem, it's a 25-point problem on your exam, you leave off control, how many points will you lose? 5 points. 5 points. Why?
That's not important to do.
Yeah, exactly. In order to have a data path, you have to have control signals going through everything. So if you don't have a controller, your computer will not work. So if you draw a computer that definitely doesn't work, you definitely haven't mastered the material, and therefore you lose 5 points. So I find that when I tell people to lose 5 points, they tend to remember that. And one time I had a student just draw a circle with control. So I was like, well, plus 5. So that was literally, and then they drew a pigeon. That was it. It was a control and then just a pigeon. So, okay, so what's the next thing we have to draw?
Your registers.
Yep, so we got registers, right? So I got read reg. I probably made that one a little. Okay, so here we got registers. So you've read reg 1, we got read reg 2, and we got write register and write data, correct? So what's going into read reg 1 from the control signal? Let's just do one other thing. Going into control, you have 31 to 26, right? So that goes into control, right? So what's this one here? 25 to 21. Okay, what goes into read reg 2?
20 to 16.
Okay, now here, remember, it is an R-type instruction. So what is going into write register?
15 to 11.
15 to 11. Do I need this multiplexer? No. Exactly. So you don't need the mux, so you just write 15 to 11. All right, so what comes down here?
15 to 0.
Okay, it's 15 to 0, but what does 15 to 0 indicate?
Your 16 significant bits.
Right, but in 15, specifically, why did we split up 15 to 0? What was important about splitting up 15 to 0? What type of instruction is that? Immediate. And what does the specific question say? R-type only. So we have that down here, but all we're doing is we're going to the ALU control, right? And then we have our 2-bit input, ALU op. And then we have our control signal here, reg write. Okay? So then what's coming in here? What are those values going into the ALU control from the instruction? This is we're combining everything. You have the opcode, which is 3126, RS, RT, RD, shift amount, and function. So this value going into the ALU is determining what we were going to use. There you go. So which values are which ones are 5 to 0 function? I answered the question for you. Okay, so you put 5 to 0 in here. Also, going into the ALU, you're going to have 10 to 6 because that is your shift amount value, right? Since you all have designed an ALU, you know. So then read data 1, then read data 2 are going to come out here. There's no I type, so I don't need that control signal as well. Make sure you label ALU. And then it's going to come out here. Now here's the interesting part. It's an R-type instruction only. What do I do with data memory in R-type instructions? Correct. What am I doing with data memory in an R-type instruction? Am I bingo? Not accessing. I'm not reading from it, or I'm not writing to it. So do I need to include it? No. So then you just go done, right? That comes from the IM. Read. And that comes out here. PC. That goes up. You have your adder. Plus, and that's 4, and that just comes back, right? That's the full data path, right? Just for the R-type instruction.
Would you connect your that ALU with your
write data?
No, not that one.
This 10 to 6, that's shift amount.
The 5 to 0.
5 to 0 is what?
Your function.
Yes, goes into ALU. Yeah, you can connect it here. Just connect it there. And how many bits is this? 4. Yeah, 4 exactly right, because that's what comes out of the ALU control. So you have a 6-bit value function coming in, you have a 2-bit ALU op coming out, you have a 4-bit value which controls the 16 to 1 mux for each bit that comes out of the 32-bit ALU and goes to write data. So here you only need reg write and ALU op. We don't need this control signal, we don't need branch, we don't need jump, we don't need mem read, we don't need mem write, we don't need mem to register because we're not bringing anything from data memory. So that's a simple one. Right? So you can look at the solution for those of you coming back here. Let me a little more. So as we see, PC plus 4, read address memory. And I said no branch equivalent or jump, therefore no further addressing. 31 to 26 control, 25 to 21, 2016, 15 to 11. We have reg write, 10 to 6 comes over here, 5 to 0 goes to ALU control. You have ALU op, the 4-bit value comes out here, and the feedback comes there. So does this make sense for this? Okay. So the next question. Draw a MIPS data path that implements load word instructions only. So let's work through that one. We have our blank page here. What do I need? What's the first thing I need? PC. PC plus 4, which I would just draw haphazardly. You can do a plus 4. And do I need anything else? What type of instruction is branch? It's not a J-type. It's an I-type instruction. So we do need more out here, right? So to be continued. So this is where you got to start thinking through everything. So then it goes into read address, instruction memory. This comes out, 32-bit value. What's the next 32? What's the next value thing that I should do? Control. And then 31 to 26. 25 to 21 for registers, and then you go reg write. And so read reg 1, read reg 2. Now, and this is 20 to 16. Now we get to this control signal. Should I use it or not? Do I need one?
Yes.
Okay, so I have an I-type instruction. Load word. What am I doing in load word?
You're loading into a register.
Correct. Specifically which register?
S0.
No, that's not no. RT, correct. So I'm going to need this here, right? Now, let's think about this. Do I need the 15 to 11? When the branch R-type, branch, load word, and store word are your main ones. Which do you need to write to 15 to 11 for anything?
No.
No.
It's an I-type.
It's an I-type because we always need 15 to 0, right? So you just put it in here, and that goes to your write register, and we'll come back to write data in a bit. So what's this value that's coming down here now?
15 to 0.
15 to 0. So do I need to put anything into the ALU controller? No. Because all it has is the 2 bits, right? ALU op. And when it's not going in there, it's just going to say ALU control. You just go straight to the ALU. And then you got read data 1, read data 2. Because we got stuff, they're both coming out, right? So 15 to 0 is going to come around here. And what are we going to do to this here first? Sign extend. And so make a little note 32 out there, right? So it's going to come here. And then what I got to do? Mux, right? 0, 1. And what's this control signal? ALU source. Very good. And so what am I going to do with this next? This line right here. From the 15 to send it.
To shift logical 2.
Yeah, shift logical 2. And we got this value coming here. And then what are we going to do? Yep. Add these together. And you put the PC around. And so now we're going to have this input into the ALU. Let me draw this out real quick. Very shabby, but it's touchscreen. So what do I do next? What's going on here? What's this one at the top? 0-bit. And so what do I do with this? So there's what's that control signal called? Branch, right? And what do I do with these two? Right? So that gives me a 32-bit value out. That comes all the way back. So then I have my, let's just try to make this as small as possible. We got mem read and mem write. So you got data memory. Then you got this control signal here because you can either update them to ALU. Here's a question. Do I need that control signal? So I have this data memory here, right? And it's going read data. I got mem read, mem write. And I have this value coming out of the ALU. Where does that value always go in an I-type instruction? So here you have, when that AND gate is set and branch is set, this doesn't matter, right? So you're never going to write back to the registers in this case. So that's going to come back and update it. So no matter what you do, it's not going to update precisely because your reg write is going to be set to 0. Your mem read is going to be set to 0, and your mem write is going to be set to 0. So therefore, no matter what happens, it won't be updated in the event of a branch. Now, we also had, coming out of the registers, we had read data 1, read data 2, and then a bunch of magic with the ALU here. So for store word, this is the read address, correct? I'm sorry, write address, right? And so so I had write data. I had to take some value from somewhere, correct? Where do I get that value from? If I'm doing a store word, I'm using the base pointer and the offset, which is 15 to 0, to calculate the write address. So what's this write data? Where am I actually getting the value to write? Exactly. Read data 2. It's going to go around the ALU and go to write data, correct? It's going to come around here. Very good. So since I'm not doing that, I don't need mem to reg, so I can just go back to write data here for load word. So to show you the answer, you guys have correctly derived the solution. Here we see we have the program counter right here. Add PC plus 4. I don't know why it says no VQ or load word. That's wrong. Let me update that answer. Oh, because did the question specifically say load word only? Okay. All right, that's why. Load word only. So no branch equivalent or store word. So we don't need the rest of that for load word. Structure memory, 31 to 26, control, 25 to 21, 20 to 16. In this case, we're just writing to the register here. You guys made the right call on making that decision for adding 20 to 16 for read register 2, so you can make that ALU decision. But here in this case, you're just sending 15 to 0 to sign extend here, and you're sending just the ALU off. You see there's nothing else coming in here. We don't care. It goes to 4, memory address, mem read, and mem write. Now, what's the next question? Is it itype? Oh yeah, that's just store word. So if it was store word, how do we change this data path? So next question is just store word. Okay. Ty, say the same thing you said. You answered my last question. What would I have to do to change this? If I'm updating the write data here, so I'm putting data here to update on a store word. So where's that value coming from? Yeah, read data 2. And so, since the next problem would be only store word, that can go away, because if it's only store word, you're never writing anything to a register. So you can just go like that. And some people have different approaches to this problem. Some people will memorize the entire data path and will try to go through that and write it all out. And then what they'll do is they'll actually have a different color pencil or a pen, and will actually make little marks through it. Other people just draw it straight out, whatever you feel more comfortable with as you're studying for this. So that was the answer to store word. As you can see, no write register, no write data. 15 to 0 goes there to calculate the result. As Ty said, it comes right to write register. Mem read is equal to 0, and then mem write. Okay, so what's the next one? Wow, everything's kind of disappeared all of a sudden. That's not good. Yeah, look at all this nothing. Good thing I have the Word document. Oh. I'll be right back. USB is upstairs in my office. Talk amongst yourselves. Discuss the peanut is gonna need no pea nor nut. Discuss.
I'm gonna watch it right. I'm sure it's gonna be easy at last. Is it? 3 of them.
Originally, they said for trying to 6 last month.
Yeah. Yeah. No. 7:30 whenever he decides to stop. Thing is, the citations are basically the test, so might as well go to the.
Y'all talk crap about me, I'll go to hear it on the video later. Your entire exam will be marked wrong and I'll just clean shaven like my face. And we've done load word, we've done store word. And now we're combining them together in example 7.4. So let me view page width. So in 7.4, we're just combining together. This one says draw a single cycle data path that executes load and store word instructions only. So again, we need PC plus 4. We don't have a branch or a jump, so we leave that off. Instruction memory, 32-bit, controller, 25. Now here, 20 to 16, I also break off 20 to 16 into write register because that's what we'll do for load word, correct? We bring 15-0 here. We sign extend to 32 bits. We do that every time. We're not going to be calculating anything else with the ALU. Read data 1, read data 2, write data. This goes to the address because our calculate, this is the base pointer. Mem read and mem write. And then read data comes back for load word. And while it's not required, you may have noticed that on previous problems I've written this stuff down here. This will help you out on an exam. If you're drawing a problem out and you just try to justify why it is you did something, and I can squint in the right way, I might be able to give you some points. So if you're unsure, try to justify your answer. So 7.4, 7.5. So here, what I've done is draw a single cycle data path that executes R-type and add-I instructions only. Right? So here, we have no branch or jump, so we've done PC4. We have instruction memory, rememory, 31 to 26, control, as always. 25 to 21, read, reg, rug, and reg, write. Same thing. 2016 goes into read, reg 2. So up to this point, everything from here that we've just done, let's say I said like branch or jump or something like that. Write register. Now here we have the control signal register destination because for R type, we have to write to 15 to 11, right? And so what do we have? What are we writing for add I? I type instruction. But what register am I? How do I tell what part of the instruction indicates what register I'm writing to? 20 to 16, correct? So this portion here coming from that goes into the register destination multiplexer, goes into write register. Here we have 15 to 0. So first we have to sign extend because we're doing addition. So if we're doing add I, what we're going to be using is this part here to add, and then this value. So that add I comes around and goes into write data. If we're doing this for R type, we're getting this value and this value, they're coming out and they're writing here as indicated by this instruction. So also for R-type, I have included the shift left logical, which is 10 to 6. And 5 to 0 goes into ALU control. So 2 bits come out, 4 bits there. Comes into the result. So make sure you remember to mark, the key ones you need to mark are 32, 2, and 4. And then when we get to jump instruction problems, you indicate 26, shift left to 28, then concatenate gives you 32. Okay. So does that make sense? 7.5. Okay, so we're about to get to pipelining. Now one last thing I want to do. Everyone take out a sheet of paper. And I want you to make your best guess. Since I already have a blank sheet of paper, I will give you guys 15 minutes. And this is not a quiz per se, but I'll try and figure out some way to make it count for credit for being here and everything. So the problem is going to be draw a reduced MIPS data path. So that's how the way it's going to be. So reduced meaning that I'm going to have some subset, right? That calculates R-type and I-type instructions. In fact, who has group members here? Okay, almost anybody not have a group. Does anybody's group members just not showed up? Karanthi? Okay, so Karanthi, can you join Olivia and McKinnon? You guys get together in your groups and try to come up with a solution to this problem. And you can put all of your names on one paper. So you have 15 minutes, group think. Just one submission per group. You know, this is a group can move over here. I won't bite. Everyone's just cramped in the back. That's upside down. I forgot about the instruction. Yeah. Don't use your notes, by the way. I should say. Try to make your best effort. Practice as though you were doing an exam or a quiz. It seems instructed I and R type. I don't think we're doing
So this goes in, so part of that goes into that.
That should be 15, right?
Is that right? Those two go into that.
It's either 2016 or 15.
Almost there.
I would highly recommend drawing it out this way. You quickly find out you'll run out of room if you do it this way.
Tell us now.
If you can fit it, that's one thing. But if you're starting to notice that it's running off the page, save yourself some trouble. You have tape, yeah. Leave them together.
From that, there's the ALU 1 and 2.
It goes there, but something. So there should be like a 5 to 0 bit. I guess I'm using some but I don't think there's technically
It goes from.
And then I think this one. This goes from that.
Here, not from the
I don't think there's.
Cool. You can change it by because the 4-bit value is the 2-bit value is the
Yeah, that's right.
Down here.
Oh man, and then this is your over there. And this comes on R2 to the end, right? It's just it's a I think that's most right now. I might have missed up around here, but Actually, I did. You know, I mean, this makes a lot of sense now. You know, 2 weeks ago it wasn't making that much sense, but yeah, what is like maybe it's except for just sleep and stuff. You know what happens is one day I learn something and I don't get it, and then the next day like I fully understand it. Because if you sit there and I mean, it's just this. You split for our time. For our time, we have actually. Yeah, for our time, it is 51 minutes. I think it's time to see it. And 5 to 0. This is our ship amount. I don't know where that goes. But that's your ship amount, and then you have your 5 to 0, which is your function. Oh, yeah. Oh, so let's bring back 5 to 0 goes to the ALU. Our time. Right, yeah. That's why you go there because it's our time. But I mean, that's the fine side. You know what? I meant to tell you if it's your high time, you go.
Yeah.
I know that because they're combined, so that's what I try about the art type. To 0, that's where the high time.
Zero in the brand.
I guess instead maybe I could put a part of that so there's maybe I'll put a part of that so it's just like an ALU. Maybe I could. I'm missing stuff. I'm missing I still can't believe I missed the rest. I know. It's reminding. I see what I wrote. You could look at it and see.
It goes up to the A gate and then the branch for the other inputs.
That's a classic example of why you want to write.
I know. Oh, wait a minute. Now maybe you could rewrite it. See if you could rewrite it too. Maybe you could rewrite it. I could help you read something. Now, if you run out of time, you still have that. He takes notes on this. Just copy paste. It says all white. That is perfect. I was also curious when I was going to I mean, like you could be though. I think you're making some sort of brand. Because instead Divide all the goods, it's gonna 20 over. We say the calculation. The reason we don't like it is it's gonna load. This output is right here. And then I remember the guy that he had this long dread like big sheet in his head. Let's string them. It's great. This is ours is red like DS. Wait, that's not red. What is it? Yeah, because it is bar and this goes into ARM architecture and other architecture.
I just want to know where you guys are at. 6 instructions. There's an adder here. Here.
Thanks. 2 minutes.
You think we do data right?
I mean, the touchscreen piece without I'm not sure. That's okay. I don't know. I forgot what to do. That's for only for art and instruction, right? Because the other one's I know definitely that. So what is an art? So you can read my paper.
30 seconds.
All right, so pass your papers to me. Make sure their names are on them.
Yeah, well,
You guys, thumbs up.
yeah. No, but the second time, like the
All right.
Yeah, rough draft is one.
So Here's the solution. Actually, you'll see that? Okay, cool. Use that. So here we have our program counter, right? Goes in here, goes up to PC plus 4 like normal. Add instruction memory, comes out 32 bits, right? So now, got a controller, so maybe you get plus 5, right? So you got reg write, because we're going to be using that for every single one. You got 25 to 21. I'm hoping I mix it. Close enough. 2016. And now, here, we have to use register destination, because we have 5 to 15, 11, 2016. Now, over here, we have 15 to 0 initially, because we have an I-type instruction, so we definitely need 15 to 0. Now, 10 to 6 comes and goes into the AOE. Add professor. 10 to 6 comes here, right? And then this comes out and goes here. Okay. So 10 to 6 goes to the ALU for shift left logical, shift right logical. ALU source comes from the sign extended 32 bits, right? Goes to 1. If it's 0, comes from read data 2. So that's an R-type instruction. Read data 1 always goes to the ALU. So for store word, we have data coming from read data 2. For branch, which is an I-type instruction, we have 0, branch, and then was this multiplexer? Common mistake, I saw it, at least one group do it where they put the branch over here and then just comes over there, right? So hopefully make the mistake now and not on the exam. So again, we have, I think it's pretty close. Okay, so here, remember to register. If it's 0, it's coming from the ALU, as you can see over here, right? If it's 1, it's going to come from data memory. And then it comes around and goes up here. And then if the screen wants to cooperate, it comes back to write data. ALU source, 2 bits for ALU up, comes out 4, goes to the arithmetic logic unit, 31 to 26 controller. So here, and then you have mem read and mem write. Okay. So does anybody have any questions about that? I think somebody had a good idea. I'll do that too.
Unless we can post it on Snapchat or something. So you guys check it out. That's why you're safe.
So anyway,
put on Pinterest.
Yeah, well, that would be why I'm single and own a lot of cats. I don't own any cats, if it makes you feel any better. So, all right, so I'm going to count this. Here's what I'm going to do. I'm going to count this as a TGO assignment to reward attendance, but I will mark it up the way I'm going to eventually grade it. So you'll get a 10 out of 10 for being here and making a solid attempt, but you'll get the marks back so you can see precisely what I'm looking for in a graded assignment. So that's my way of rewarding your attendance instead of whining about people not being here. Okay, so pipelining. So we've done 7.1 through 7.5 so far, right? Okay. So let's do some pipelining. Now, up to this point, so that what we just went over is where your final project is going to end. You're going to combine everything together. You're going to write it out. I'm going to do the type up, so it's going to be 3 stages throughout the rest of the semester. Now we're getting into improving performance. So up to this point, we have all these stages. We have instruction fetch, instruction decode, execute, memory, and write back. But they're all just doing one instruction at once, right? So that means whenever we are putting something in data memory, the rest of the data path has nothing, it's not doing anything. We're not calculating the program counter. We're not doing anything else with it. So this whole idea with pipelining is we're going to be trying to use the whole data path simultaneously. And since we have 5 stages, we can have at most 5 instructions in the data path. So we're going to be learning about that. We're going to learn now. When you try to do that, that comes with some challenges, and we're going to be learning about these things called hazards, data structural and control hazards. So the basic concept of pipelining: we're dividing the data path into nearly equal tasks, and then what we're going to do is we're going to be putting buffers between them, between each stage, to make sure that they actually do the exact same amount of time. Dividing the data path into nearly equal tasks to be performed serially and requiring non-overlapping resources, meaning that you can't have 2 instructions using data memory at the same time. You can't have 2 instructions using the ALU simultaneously. Next, we want to insert registers at task boundaries in the data path. So what I mean by registers is between instruction fetch and instruction decode, you're going to have a buffer. So it's going to be some amount of time it's going to hold until the next clock pulse comes through, and then you start again. And then I'll be describing how this works in more detail. Registers pass the output data from one task as the input task to another. Synchronize tasks with the clock, having a cycle time that just exceeds the time required by the longest task. So what that means is, if you look at instruction memory, you're accessing memory, you're adding insert cycles back, right? Instruction decode, you everything, you go to the controller and it goes to the registers. Execution, you have the ALU, and then you have data memory, and then write back. So all of those are going to take different amounts of time. Previously, what we would do is you would just add them all together, and your clock cycle would be as long as how all of them went. So instead, what you want to do is you want to take the longest one and make that the length of the clock cycle, and then use those registers in between. So if, let's say, instruction fetch takes 3 nanoseconds, and data memory takes 5 nanoseconds, and data memory happens to be this longest required resource, what's going to happen is we're going to put this register in between instruction fetch and decode, lasts 2 nanoseconds. So that way they're all 5 nanoseconds. Now normally if you have 3, 4, 4, and 5, and 2, then suddenly that's going to add up to 8, 10, 13, 18. So your clock cycle goes from 18 to 5. And then you're putting more instructions through. And then break each instruction down into a fixed number of tasks, as you now know that is 5 next, so that instructions can be executed in a staggered fashion. And so, comparison of single cycle and pipelining execution times. So, if we were just doing single cycle, we do load word, right? Load word, in this example, they're all 2 nanoseconds for instruction fetch, instruction decode, execute, memory, and write back. So that's a total of 8 nanoseconds. We were saying that the store word will write back. We're not writing back to the registers, correct? So it only takes 7 nanoseconds. R type doesn't access data memory at all, so it only takes 6. And they have B format in this table, but that's branch equivalent, branch not equal. It would take 5 nanoseconds because you're not accessing the data memory and you're not writing to the registers. So, that went really fast. So this is what happens. The execution time in single cycle just looks like this. It takes 8 nanoseconds, 8 nanoseconds, and 8 nanoseconds because you set it to the length of the longest one. So 3 instructions will take 24 nanoseconds. So what happened if I was trying to use pipelining? Well, now we break it up this way. Let's see if this will work. It does work. Okay, good. So execute instruction fetch. When we get to instruction decode, we just have instruction fetch in the next stage. Execution memory and write back, like so. And so instead of taking 24 nanoseconds, we've now locked it down to 14. And here at the bottom, they have a performance equation where 24 divided by 14 is 1.7, so you have a speed up of 1.7. So that's an ideal situation. So this 7.6, where'd it go? I deleted it. All right, so let me give you a hint. You will see this problem again. The point of this problem is for you to demonstrate mathematically that you understand the ideal speed up between pipelining and single cycle instructions. So assuming n computations, so you have an instance where you could have 1,000,000 computations, whatever. K stages, which in MIPS would be 5, in an ideal simple linear pipe, and TSC is the clock period, so that's time single cycle. Derive the equation for speed up compared to a non-pipe and its throughput, where the clock cycle for each single cycle is TSC and pipeline is TP, right? So we go back to section 1. We're going to use our speed up equals single cycle over pipeline to get our performance. So how do we calculate single stage? So we have the number of instructions times that single cycle, right? And we showed you that single cycle ended up being 8 nanoseconds in the example because it went to the whole length of the load word. So times the number of instructions. For pipeline throughput, it's stages. So we have 5 stages plus computations minus 1 times time is k plus n minus 1 times T of P. Now here is what I mean by that. So let me give my spiel on how this works. So you have your first, go over it. Okay, so we have our first instruction, right? So we have instruction 1, and that's in fetch, decode, execute, memory, and write back, correct? How many stages does that take to execute? 5, right? So we're at 5. So we have next instructions. So this is 2, instruction fetch, decode, execute, memory, and write back. This is 6, 3, write back is at 7, and 4. This should be sufficient to show everything. This will be at 8. So we now know the relationship. Here you say it's plus 4, right? 1 plus 4 is 5. 2 plus 1 is 6. 2 plus 4 is 6. 3 plus 4 is 7. And 4 plus 4 is 8. So why is that number 4 important? Because we have the one instruction relating instructions to end cycle. So we start with 1. Now it's k instructions, right? So you have k plus this number is 6. K is 5 plus 2 is 7. K is 5 plus 3 is 8. So it's off by 1, right? So in order to account for that, we subtract 1. And the reason why it makes sense is because you start with 1 there. So the actual throughput, I'm sorry, go away. Nope. We're having a day with the computer here. So we have k plus n minus 1 for pipeline throughput. And then you set these up, n times TSC, k plus n minus 1 times pipeline time. Now, the throughput is the last part. So what you do is you keep adding instructions, keep adding instructions, keep adding instructions. For the next data path, it's going to be 5. You start adding 1,000,000 instructions, 2,000,000, 20,000,000. Eventually, you're going to get a point where n gets much, much greater than k. So here's what's going to happen. Eventually, n and k plus n minus 1, because remember k is 5, so it's going to be 4. So these are essentially going to cancel out. Right? So you're going to get TSC over T of P as n gets significantly larger, right? Remember limits from back in count 1? So what is this relationship here? What's that approximately going to be? The difference between the single cycle clock length and the pipeline clock length.
There's a performance ratio.
Yes, and what is that approximately? Going back to, if we have single cycle, how many instructions do we have in the MIPS data path? Just single cycle. Single cycle. Single cycle. Okay, three wasn't even close. I would have said 3. And I have a single cycle data path, which would do just about 1, right? So if I have a pipeline data path, how many instructions can I have? 5, right? So if it's going to be 5 over 1, is going to be that ratio. So for a data path where you have k stages, what's this value going to be? K, right? So it's going to be k over 1, which is why we can say that the limit, as the number of instructions approaches infinity, equals k as n gets much, much greater than k. So the whole goal of pipelining is to break it up into stages, and that ideally that improvement in throughput should be k. So we can keep going and show an example here. So basic single cycle data path, you have your 5 stages, right? And then pipelining with buffers. So now we're putting everything in between them, right? So we have these registers here. If you go back to the stages of pipelining, the principles of pipelining, 2 nanoseconds, waits, 3 nanoseconds, waits, 2 nanoseconds, waits, 4 nanoseconds, that was the longest one, so it just goes right there. And then instruction fetch. Now you're breaking the stages. You get everything back from your multiplexer. The program counter gets everything from instruction memory. And then this would go, if you want to deal with the next instruction, you just go back. Now, something we can think about before we go to next class, what's the potential problem with this? If I just have the PC plus 4 automatically go back to be picked up by the next cycle. Branch instructions, right? So what happens if it's a branch? I won't know until the 3rd stage whether or not I want to branch. So that is an example of what we call a control hazard. Trying to figure out, can we properly control it? We don't want to execute instructions while that weren't supposed to be done. So instruction decode, we read from the registers and put it on the buffer. We're not writing to the registers yet. This is what this notation means. The white means it hasn't been read to, and blue means it has been. When we get to write back, you'll see the blue is on the left and the white will be on the right. Execution stage of the data path. We get everything from multiplexer, shift left by 2. We get everything from the add, ALU. We put all those results on the buffer. And then the memory stage of the pipeline data path, we get everything from there. We do our load word, store word type stuff and put everything on this buffer. And then at the end, you will see that it writes back, and then we put it into the write portion. And so here's what's actually going on here. And so this will end here. So we did 7.1 through 7.6 in TGO 17, right? I lost my chalk. All right, so for the rest of the couple minutes that we got, we have kind of this notation now where we're reading from instruction memory and putting it on the buffer, register, we're reading, ALU, and so forth. So this is kind of how each data path is working. You can see that in subtraction, we're not accessing data memory at all because there's a write to data memory, so you see it's all white here. For ALU, we're always accessing the ALU every instruction. And for write back, you see a reg and regger here, the same. So here, except we have it on the right, meaning that we're reading from the register and putting it onto the buffer, whereas from here, we're reading it from the buffer between data memory and writing back. So that's the notation. So this is an ideal situation. Now, what's there some issues that could happen, do you think? We already discussed one. We called it a control hazard, right? Any ideas? Let me give you a nudge. So let's say that I have sub, and the result is supposed to go to register 5. But here in the next instruction, I need 5. What's going to happen here is that the result that we want is going to be on this buffer, and it hasn't been written back to the register, but then we're reading from the register onto the ALU. So that's what's known as a data hazard. Also, the third type is called a structural hazard, where you have 2 instructions trying to compete for the same resource at the same time. Which means, let's say I had stage 4, I was going to data memory, but I'm also accessing the instruction memory in a situation where they were the same memory. Remember how I told you earlier in the semester that instruction memory and data memory were separated to eliminate a problem? This is that problem. I'm trying to get, because if you think about it, if you're calculating the ALU and you go to PC, you have a read address from an instruction and a data memory port. And you're trying to access the same array with 2 pointers. And that's a structural hazard. So the 3 types are data hazard, structural hazard, and control hazard. So these are the types of problems that could arise. And we're going to start next lecture. I bet the next TGO 7.18 is define pipeline hazard. And yep, that's exactly right. So I just got to get right at that. So there's your homework assignment. I'll post the video. I'm going to be on the other side of the campus working at a conference today, so I won't be around very much. Give me 1 split second.